I may have just gotten in. Let me see if I can make this work. Nope, it's not working. Nope, I do have students now. So this is, yeah, this is 15 minutes into it, but I finally got in. And all I do is keep doing the same thing and eventually something works. But I don't know why it's making me do it over and over and over again every time. Does that make sense?
Yep, that makes sense. What I was going to say is I have been taking notes on your issue, and I've seen you've had tickets before put in, like you said.
Yeah.
I can send this ticket to the Zoom team and ask them if there's any, thing they need to do to, make sure you're not having this problem, and see if, there's something you can do to get it easier.
Yeah, and I may, because I'm doing this again next semester. I really would prefer, if I could get this resolved, I would love to get it resolved, because like right now I'm starting class almost 20 minutes late. Because I can't.
I do apologize about that.
No, it's not your fault. I just don't understand what's going on this semester that hasn't gone on in the past.
Yeah, I understand, and I hope this problem doesn't continue. Hopefully it will get to stop soon.
Yeah. Well, Tyler, I really appreciate it. I do need to get going with this class now that I'm finally in it.
All right, no problem at all. You should see a ticket in your email with that information about my phone call. And like I said, someone should reach out to us, letting us know what they can do to make sure we don't have this problem in the future, okay?
Okay, thank you. Have a wonderful day, okay? Happy Thanksgiving.
You too, thank you.
Thank you. Bye-bye.
Bye-bye.
Hi, good morning.
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 I don't know what the issue was. I finally, after trying for 10 minutes or so, I finally called the Hack IT Tech again. I've called them a couple times, but they haven't been able to help me. But this morning it was just taking, as you can tell, a really, really long time. And all I do is keep going in through our syllabus and our Zoom link over and over and over again. And eventually one of them works. But this morning it took over 20 minutes, which is a really, really long time. Let me answer an email from a student. I'm not sure who it was, but if they're not here, let me see if I can't get them. Jesse, you're here. So you're the one who sent me this email.
Yeah, sorry. I just wanted to make sure I wasn't missing anything.
Nope, you're not. Genesis is here and you're not missing anything. Okay. Yep, that's only two. Okay. Yeah, I don't know what the issue has been. Normally, if I just keep trying, eventually one of them lets me into the class, but it did not work this morning. First, are there any questions or concerns outside of the fact that class started really late?
Did you only post chapter 16 this morning?
I posted it last night.
All right. I went to look for it last night. I just didn't see it.
16. I posted it last night.
Okay.
It's actually been posted for a couple days.
Okay, it must have just been my phone because I was looking to print it out last night, but I was looking on my phone before I made the drive down to my mother's house, which is an hour. So that's why I must have missed it. That's my bad then. I'm sorry.
No, don't worry about it. I didn't really, one thing that I'm going to make very different between now and next semester is change the way things are organized on here, because we've kind of had a weird, things have not been on schedule. This week one, week something or other doesn't work for this class. And I should have arranged this in chapters rather than weeks, because I keep moving things around because we're behind in weeks. And I can't imagine that it's not confusing for you.
Yeah, I was actually gonna ask you about that because I noticed, like, I try to keep
Who
up
is
with
this
my
talking to
assignments.
me? Can you tell me?
Michaela.
Okay.
Yeah, I try to keep up with my assignments, but I noticed like I won't know when things are due, or like I'll get like the due dates mixed up.
Do you have them on
Um,
the content or course page when they're due right here? Do you have them here?
yeah, but the due dates literally switch around. Like
Well,
I'll check.
I switch them around when I push them back. I am pushing them
Oh,
back. This
okay.
one, I am pushing them back.
Okay, because I was like, wait a second.
But if you have gone in and realized that a deadline has passed for something, send me an email, tell me what assignments, when you think you will have it done by, and I'll extend it out for you.
Okay. Okay, so I'll do that later.
Yeah,
then.
that's just, but I need to know the name of the assignment, specific name of the assignment, and when you will have it done. And I'll extend them back for you.
Okay.
Professor, was lab 21, that is due tomorrow, correct?
Yes.
Okay.
Yeah, all of the Wiley labs, when we cover them in lab the week before, if we cover them on any given Thursday, they are due the following week, Wednesday at midnight.
I just forget because it's not posted on the side, like if you don't
No,
literally go back in and click on the week,
it's
it's
not,
like out of sight, out of mind.
it's not, and that's kind of, that's the way Wiley is set up with D2L. And there's not anything I can do about that. It's the way that McGraw-Hill, when they're linked to D2L, this is how they link up, where they show you the due dates. Wiley doesn't link like that. And I don't know why, but there's not anything I can do about it either.
Oh, I know. I was just telling you, that's probably why a lot of us just
I
forget.
understand. I understand. I've tried to stay consistent with those deadlines, and we aren't behind in lab. And so when we do it the week every Thursday, when we do it, it's due the following Wednesday. And if you do miss things, that's still okay. Just tell me, send me an email, tell me when you'll have them done, and I'll extend them out. It's not that hard for me to extend them out. Other questions? Okay. We will finish. So I put chapter 16 in front of chapter 15. We really could have gone either way with this, but I wanted to make sure that I made it through chapter 16. If I do the chapter 15 as a recording, it's pretty easy to comprehend. There's a lot of material there, but it's short and it's fairly easy. It's not more abstract concepts. It's more, this is this and that is that, and this is what it does. But I decided to do chapter 16 and then do chapter 15. But we still might be able to get through both of them today and finish chapter 16 and finish chapter 15 today. You'll see they are not very long. So let's get started. Let's see what happens here. So middle ear infections in children are much more common, partly because as the face elongates out, the eustachian tube that works to clear out the middle ear and drain it into the nose, the fluid, any fluid drains into the nose, becomes more vertical as you age. And therefore gravity works to pull the fluid, drain the fluid into the nose, rather than let it get trapped in the middle ear and cause an infection. So infections of the middle ear, which are the most common ear infections. I don't know of other common ear infections. Or when fluid accumulates in that tympanic cavity, the middle ear, producing pressure, pain, and impaired hearing. It can cause fusion of the ear ossicles. Remember, those are the 3 bones within the ear, little bones within the ear. A lot of times, one of the treatments for chronic ear infections is a tympanostomy, which is where you lance the tympanic membrane and insert a tube, or you can, sometimes they will just lance it. Other times they will lance it and insert a tube. But the main goal is to drain the fluid from the ear tympanic cavity. And it looks essentially like this. Here's the tympanic membrane. And if you look here, right here, you can see the head of the malleolus actually attached to the tympanic membrane. So it's just working to drain the fluid out of the ear. One thing with having grown up with having them insert tubes into my ears all the time, I probably had it done probably 12 times, is you cannot get the inner ear wet. There's ways to wash your hair and so forth to avoid getting water into your ears. Because if that fluid gets caught into the middle ear, it can cause a really nasty infection. So we covered the middle ear and the outer ear. The inner ear, which is essentially where the hearing and balance are going to occur. If you remember, let me skip back a little bit here. The middle and the outer ear are involved in the transmission of the sound vibrations. That's their whole function. The inner ear is where we get a conversion of those vibrations to nerve signals, a series of action potentials. So the inner ear is a tube within a tube structure. The bony labyrinth is the outer structure. And within that outer structure, the shell-like structure, cochlea meaning a shell-like structure, there's a fleshy membranous tube that these float within the bony labyrinth. The inner fleshy tube is filled with what's called endolymph, which is similar to intracellular fluid, like your cytosol or your cytoplasm. this inner tube of the membranous labyrinth is going to float within the bony labyrinth, which is filled with perilymph, which is similar in its composition to cerebrospinal fluid. The cochlea is the organ of hearing. So it coils around a screw-like axis of spongy bone, which is called the mediolus. The vestibule and the semicircular canals are the organs for equilibrium and balance. So here's the middle ear. Here's the outer ear that would be right down here. Here's the cochlea. Here's the semicircular canals. And the vestibule. Within the cochlea, there's three separate chambers. There's a middle chamber, which is called the cochlear duct or the scala media. So this is a cross section through here. This is a scala media, which is the middle chamber, and it's filled, like it said, it's filled with endolymph. So this is that. So remember, we're dealing with a tube within a tube. Here's your inner tube that's floating in the outer tube. Here's your inner tube, the blue one here, scala media. It's floating within the outer parts. It is separated, this inner tube. If you want to think of it, it's like a bicycle tube. Your rubber tube is within the tube of the second. You know what I'm referring to. You have the bicycle tube, and then you have the outer bicycle wheel. The bony labyrinth is the outer bicycle wheel. The rubber tubing that's within the bicycle wheel is this inner fleshy labyrinth. So it's separated from the two outer parts of the tubing, from the scala vestibuli via the vestibular membrane. And it's separated from the scala tympani down here by the basilar membrane. This is going to be important in a moment. Within the cochlear duct, the scala media, is the organ of Corti, which is the acoustic organ that's going to convert the vibrations into nerve impulses. So here's the cochlear duct, here's the scala vestibuli, here's the scala tympani, here's the organ of Corti, which is enlarged right here. Within the organ of Corti, there are hair cells and supporting cells. The hair cells are the receptors. So they have long, stiff microvilli called stericilia on their apical surface. Remember, apical means on top surface. And they sit or are embedded on top within a tectorial membrane. We have 3 rows of hair cells. Sorry, 4 rows of hair cells. We have 3 outer rows and 1 inner row. These hair cells are the receptors for sound. If you lose these hair cells, if someone loses these hair cells, you no longer will be able to hear because
Can
you're
that-
losing the receptors. Go ahead.
Can that happen because like you listen to too loud of sounds or certain octaves?
That's a little different, and we'll talk about that here in a moment. It is a little different. Did we already? I don't think we did.
Because I have some hearing loss. I'm just kind of curious why.
Have you ever been evaluated, Erin?
Just at the doctor, regular doctor's office, and they had no idea what was going on. But I have certain octaves that I just can't hear anymore, and I do a lot of lip reading to supplement.
Erin, go into a hearing aid specialist and they will do a free hearing evaluation on your ears.
Yeah, I didn't know they did that. That's awesome.
Yep.
Thank you.
They do it. And I believe me, I've been there more than a few times. And so they're going to try to sell you a hearing aid. But do you have any has a doctor ever seen any signs of infection?
No, I mean, I had some ear infections growing up, but I've been working around heavy machinery and ambulance sirens and
Okay.
fire department, like a lot of loud noise. That's why I was curious if you would like damage the hair so it didn't receive certain sounds or something.
You're more likely to damage the bones, the ossicles.
Okay.
But I do know, I told you my best experience when it comes to the special senses, the reason I chose hearing is because it's the one that I know the most about. I think I talked about a friend of mine who got the tip of her nose torn off with the trampoline springs, and with that she no longer can equalize the pressure in her middle ears via her auditory tube. She had a rare autoimmune disorder, that an autoimmune meaning that your immune system is attacking your own cells, that destroyed her hair cells. And so she learned how to speak before it occurred, but between the ages of 5 to 18 years of age, she lost the hair cells in her ears. She's still got some, I'm guessing, because she does hear sometimes. She hears a few things. But it was an autoimmune that attacked these, and these are essentially the mechanoreceptors that are sensing the vibrations and initiating the action potentials. And Erin, we will talk about that here in a moment, how you might be struggling with that based on whether it's loud sounds. You could be struggling with what I've dealt with, which is chronic ear infections that resulted in the otosclerosis, meaning the the bones had partially fused.
Okay.
But it could be a lot of things. I mean, I should, and I'll have to add this to my next time that I teach. My hearing evaluation, which is kind of all over the place. I don't hear in the lower tones. Or is it that? Yeah, I don't hear in the lower tones. And when I went in for a hearing evaluation, the only thing the lady behind the technologist that I was working with, she was like, your hearing loss is all wacky. She's like, it's all over the place. But Erin, if you go in any hearing aid place, will you give you an evaluation?
Okay. I'll have to do that sometime.
Yeah, because they're trying to sell you hearing aids, but they will give you an evaluation. Where do you live?
I'm out in Hershey area.
Okay. I don't know exactly where that is. That's the sad thing about not being from Pennsylvania.
It's Harrisburg. You go due east for like 25 minutes.
I'll give you a name and a number after class, and you can contact them and see if there's someone you'd want to reach out to and have it done.
Okay, thanks.
Because I really like who I worked with over the summer, and they have multiple offices. But so there's 4 rows of hair cells. There's outer rows, 1, 2, 3 outer rows. And they adjust the response of the cochlea to different frequencies. So they're involved in cochlear tuning. Kind of like when you get a piano tune, they're going to be involved in just changing the strings a little bit. Kind of people who have tuned a violin, they're just adjusting the strings a little bit to increase the precision of the sound. Inner hair cells provide for the hearing. So 3 outer rows of outer hair cells, 1 inner row. And then this gelatinous, so almost like Jello, gelatinous tectoral membrane overlies on the hair cells. Here's that basilar membrane. So here's the basilar membrane. Here's the tectoral membrane. It's the basilar membrane. Here's the tectoral membrane. Here's the hair cells. Here's the 3 outer rows. Here's the inner row.
Thank you.
And they're kind of a little submerged in this upper tectoral membrane. The scala media, remember that's the fluid within that cochlear duct, has a high potassium content. Keep that in mind for a moment. So coming back and a little bit about what Erin was asking about. Tympanic membrane has here's the cochlea, here's the tympanic membrane. Here's the outer ear, here's the middle ear. Here's the three little bones, the malleus, the incus, and the stapes. The tympanic membrane is right here, and it's attached to the handle of the malleus. The foot plate of the stapes is attached to the oval window And then there's a round window below that kind of has a little bit of give to it to help alleviate the vibrations. And here would be the basilar membrane. And remember that on the basilar membrane sits the organ of Corti. So the ossicles, those three little bones, are going to concentrate the energy of the vibrating tympanic membrane onto the oval window. They're going to start vibrating at the same frequency as the tympanic membrane. And they work to concentrate that vibration. They also lessen it, but they concentrate it and lessen it at the same time as a safety mechanism. Because the sound vibrations actually could injure your ear. So they work to concentrate it and at the same time lessen it and focus it. So the ossicles and the muscles, which are the stapes and the tensor tympani, have a protective function. If at all possible, they will work to avoid damaging your ear through this tympanic reflex where the muscles will actually pull back. They'll keep these bones from vibrating too much. So they're attached to these bones, and when the noise level is too high, they will pull on these bones to prevent you sustaining damage to your ear. Now, in the case of Aaron, it could be two different things. It could be that you struggled with ear infections as a child, or it could be that, yes, you have damaged those hair cells. It depends on which, or it could be a combination of both.
Okay.
So the ossicles and the muscles perform this tympanic reflex. We talked about how reflexes are protective functions. This is a tympanic reflex to protect the ear by pulling on the bones and preventing them from overly vibrating. Lessening the transfer of how much energy is going into the inner ear. So the vibration of those ossicles causes pressure waves within the endolymph. Actually, I'm sorry, I'm saying it wrong. They cause vibrations within the perilymph. So they cause pressure waves in the perilymph, in the inner ear fluid. This results in a vibration. So we have a vibration of this bottom membrane. If we come back up, bear with me, come back up right here. Those vibrations are being pulsed just like a ripple in a pond of water. You drop the rock and it vibrates out. That's what's occurring here. And as the fluid vibrates, the perilymph is vibrating. It's causing this membrane to go up and down. It's causing this membrane to go up and down. when it's going up and down, the hair cells are going to be moving with the vibrations of the basilar membrane. And remember that they're kind of stuck in this gel-like substance. And so they start bumping up and down to the vibrations, to the beat. And as they bump up, they're going to, it's going to open channels in the hair cells that are going to result in action potentials being initiated, because it's going to open ion channels. So it'll open ion channels, which are going to initiate an action potential. Every time you let in a certain amount of potassium because of the vibrations, boom, 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 it's going to allow for more potassium to enter, causing depolarization of the membrane, causing a new action potential to be initiated in a rhythm. So the stereocilia of the outer hair cells that are bathed in this high potassium fluid, the endolymph, are going to be creating this electrochemical gradient. Outside of the cells is plus 40 millivolts. The inside of the hair cells is minus 40 millivolts. And the tips are embedded in that tectoral membrane. As the basilar membrane is bouncing as with the vibrations, it's bouncing. Okay. As it's bouncing, you're going to be opening channels. The top one gets bounced first, and then it opens the next one and opens the next one. This one gets topped, it's attached to the second one by a tip link. Here's your 3 separate hair cells. It gets bumped, it opens up the next one, which opens up the next one. So the stereocilium on the inner hair cells are going to be connect one ion channel in the sidewall to the next one. So the tallest one is the one that gets bent when the basilar membrane rises up toward the tectoral membrane, but because it's attached to the others, they all open. Is this clear? Please ask me questions if you have them. So the ossicles are vibrating. They cause a vibration of the fluid within that cochlea in the perilymph. And the basilar membrane that's sitting within that perilymph is going to start vibrating at the same vibration. And because the hair cells are sitting on top of the basilar membrane, they are going to vibrate. And as they vibrate, they're going to get pushed up against this tectoral membrane, which is going to open the channels. Because as this one gets pushed over, it's going to open up this one, which is going to open up this one. talked about how we have mechanoreceptors that open up, mechanical channels that open up with a mechanical change. That's what this is. The channels are opening up because they get bumped. And they get pushed, and that's what opens them up. So as the tallest stereocilium is bent towards the tectorial membrane, it pulls on the tip links and opens up the other ion channels. And potassium flows in. This depolarization causes a release of the neurotransmitter and stimulates the sensory dendrites and generates action potentials in the cochlear nerve. Vibrations in the loudness amplitude is going to cause vibrations in the intensity of the cochlear vibrations. Remember that this is the tube straightened out. So it's like a shell, but if we roll it all out, it's going to look like this. Just like some people make croissants for Thanksgiving. If we roll it all out, it's a flat triangle. But if we roll it all together, then it looks like a shell. This is it rolled all the way out. So the soft sounds are going to produce relatively small motions of that basilar membrane. The louder sounds are going to make the basilar membrane vibrate more vigorously. If there's small ripples versus very big ripples. So louder sounds, as it's going to be much bigger ripples, is going to trigger a higher frequency of action potentials. And the brain interprets this as being a louder sound. The pitch, remember, loudness is amplitude, pitch is frequency. Pitch depends on which part of the basilar membrane vibrates. Is it the outer, is it the very distal end or the very proximal end? At the proximal end, where the membrane is attached, is narrow and stiff. If that membrane vibrates, the brain interprets that signal as being high-pitched. At the distal end, the membrane is a lot wider and it's more flexible, and the brain interprets that as being a lower pitched sound. If you think about it, you've got a piece of paper. A piece of paper. The part that's right next to my hand is going to be more narrow and stiff. The part that's the distal end is going to be more flexible and it's going to vibrate a lot more. So if the basilar membrane vibrates towards where my hand is, towards where the middle ear would be attached, the brain is going to interpret this as a high-pitched sound. If it vibrates towards the very outer end, the brain is going to interpret that as a very low-pitched sound. Any questions? So this sensory pathway of the neurons, we have, like, remember when we were looking at the sensory neurons in the nervous system in chapter 13, we had first order, second order, and third order neurons and fourth order. Here we have first order, second order, third order, and fourth order. The first order are going to run from the cochlea to the medulla oblongata. From the medulla oblongata, in second order, the axons can travel to either the superior olivary nucleus and the pons, or the inferior colliculi in the midbrain. Do you remember when we were talking about in chapter 14, what are the inferior colliculi involved in? What do they do? What's their function? Somebody look it up for me. What's their function?
Main auditory center for the body.
They kind of. What else are they involved in? What else?
It's part of the midbrain.
It is. What is its function? What does it do?
It
What
says
do we-
serves as the main auditory center for the body. It acts as a channel for most all auditory signals in the human body.
Right. And it's involved in your auditory reflexes. But yes, so Jesse, you were partly right. Rachel, you were right too. It's involved in your auditory reflexes. That startle reflex, that's the inferior colliculi. Your major sensor for your brain is your auditory cortex in the cerebral cortex. So first order from the cochlea to the medulla oblongata, second order from the superior olivary nucleus or the inferior colliculi from the medulla oblongata. Third order from either the superior olivary nucleus or the inferior colliculi is to go to the thalamus. Fourth order is from the thalamus to the primary auditory cortex. Where's the primary auditory cortex? Somebody tell me, where's the primary auditory cortex?
Temporal lobe.
It's in the temporal lobe. So the first order neurons from each of the cochlea are going to synapse on second order neurons in the cochlea nuclei on both sides of the medulla oblongata. The second order neurons are going to take one of two pathways. They're going to ascend to the inferior colliculi of the midbrain, which is where you have sound location, fluctuation in pitch, and auditory reflexes. Or they're going to be involved in, they're going to ascend to the superior olivary nucleus and be involved in binaural hearing. And Erin may understand this if she's got a hearing deficit in one ear. Binaural hearing is where the signals from the two ears compare how long it takes for that sound to reach each ear. And that allows you to localize that sound.
I'm about equal in both ears
You're
for
about equal?
damage, so
I know that I struggle to localize sound. I'm better when I wear my hearing aid, but I will struggle to localize sound when I'm in a classroom and I have, you know, a student who, especially where now that we're all wearing masks, if I'm not looking up and seeing when they're talking to me at that moment, I won't be able to tell where the sound came from in the classroom. I won't be able to say what direction it came from. Based on the fact that one of my ears does not vibrate as well as the other one does, conduction wise. And so it takes a little longer for it to get to that ear and get into the cochlea of that ear. These are also, this superior olivary nucleus is where we're going to get the tympanic reflex. It's going to be involved in initiating the tympanic reflex by sending out afferent fibers to those muscles that are involved in pulling back the ossicles when the vibration becomes too much. The third order neurons begin in the inferior colliculi and will synapse on fourth order neurons in the thalamus. And the fourth order neurons are going to travel to the primary auditory cortex at the superior margin of the temporal lobe. And they're going to be, that is where you're going to get conscious perception of the sound. Like we talked about before, reflexes happen before you're consciously aware of them. That's why conscious awareness occurs after the reflex has already occurred. You've already moved your head towards the loud noise before you recognize how loud the noise was. And what the noise was. Questions? Two basic types of hearing loss or deafness. There's conductive deafness, which is where the conditions are going to interfere with the transmission of the vibrations into the inner ear, which is usually caused by a damage to the tympanic membrane, otis media, meaning ear infections, blockage of the auditory canal, the outer ear, or otosclerosis, meaning the fusion of those ossicles. In one of my ears, I have a combination of the tympanic membrane, ear infections, and otosclerosis. And the reason I know that is because the tympanic membrane, it may not be damaged anymore, but because I had tubes put in my ears chronically, when I was about 13 or 14, they finally decided that, you know, I'd been wearing tubes long enough and let's stop wearing them altogether. And when they went in, as you saw, when they put in tubes with that picture above, They lance the membrane and insert that tube. And then eventually the tube falls out. Well, in the case of my ears, because I'd had them put in so many times, normally that hole immediately will start to heal up. It just immediately covers up and recovers. Well, my eardrum and my tympanic membrane, rather than closing back up again, it started growing out, and which would have resulted in permanent deafness. And so what they did is they finally went in and grafted in a new eardrum and grafted in a new tympanic membrane. And I've seen what it looks like, and it's very funky looking, but you can tell that it's been grafted in there and that it's not, it doesn't look like a normal smooth eardrum. It looks really quite funky looking. That's the fun thing of going to see hearing technologists, Erin, is sometimes they can show you really neat things about your ear. But when they went in and they grafted that new eardrum in, they realized that those three little bones were partially fused together. Whether they're like that in the other ear, we don't know, because they had tubes in both ears growing up. Whether the bones are partially fused in the other ear, we don't know. We just know that they are in that ear because that's what they saw when they went in and grafted in the new membrane. The most common form of deafness is sensorineural nerve deafness, which is death of the hair cells, like Erin may have a combination of, or any nervous elements that are concerned with hearing. So this tends to be factory workers, musicians, construction workers, etc. Questions? What I want to do right now is I want to watch a video about the cochlea. You'll see I have a few videos attached to this one today. But I want to watch the first one that has to do all to do with the cochlea. Bear with me here. Okay, there it is.
To hear, our ears must capture sound, transmit it to the organ of Corti, and translate it into neural impulses to be delivered to the brain. The organ of Corti is located in the cochlea, a spiral, three-chambered, snail-like structure, 10 millimeters wide, within a bony matrix.
So you guys, it's about 10 millimeters, which is a centimeter wide.
The organ of Corti extends from the anterior part of the vestibule and coils for about 2.5 turns around a bony pillar called the modiolus. In cross-section, the uppermost chamber is called the scala vestibuli. The oval window is situated at the base of this chamber. The lowermost chamber is called the scala tympani. At the base of this chamber is where the round window is located. Both the scala.
So remember, the oval window is the one that the stapes is attached to.
At the base of this chamber is where the round window is located. Both the scala vestibuli and scala tympani contain perilymph. Between the scala vestibuli and scala tympani is the scala media. This houses the organ of Corti, which is referred to as the receptor organ of hearing. The scala media is filled with endolymph. The scala media includes structures from the tectorial membrane, basilar membrane, and hair cells, which sense the mechanical forces. The hair cells are located between the tectorial and basilar membranes. Approximately 16,000 hair cells are within the cochlea. There are two kinds of hair cells, inner and outer hair cells. 95% of the afferent fibers are from the inner hair cells, the sensory receptors that communicate with neurons from cranial nerve 8. Outer.
Remember that these are the ones, these are involved in the cochlear tuning, so precision. These are the ones that you're getting the hearing from. That's why she says that most of the afferent fibers, remember those are the sensory nerve fibers, are coming from the inner hair cells.
Outer hair cells receive mostly efferent input from the superior olivary complex. The filamentous structures that connect the tips of adjacent stereocilia are known as tip links.
Where was that superior olivary complex found? Where was that superior olivary nucleus found? Somebody go back and tell me. Where was it found?
Is it posterior?
Nope. Where is it found within the brain? Go back a few slides and tell me where it was found, Jesse.
Temporal lobe?
Nope. Go back and look a few slides and tell me where it's found.
In the pons.
In the pons, correct. The primary auditory cortex is in the temporal lobe. That's where the fourth quarter neurons are going to synapse.
These are thought to amplify the forces in the area of the molecular sensors. How does sound enter the cochlea? Compression hits the tympanic membrane, causing the stapes to transfer force to the oval window. The sound travels down the scala vestibuli, around the helicotrema, to the scala tympani, allowing its fluid perilymph to mix. From there, sound moves to the round window. High frequencies are encoded at the base, and low frequencies at the apex. It is this property that leads to the tonotopic map along the basilar membrane. The manner in which the basilar membrane vibrates in response to sound is the key to understanding cochlear function. The hair cells are located between the tectorial and basilar membranes and are stimulated by the shearing force between the two caused by the pivot point of the two membranes. The pivot point of the basilar membrane becomes displaced. The tectorial membrane moves across the tops of the hair cells, causing the stereocilia to bend. The ionic environment of the compartments plays a critical role in signal transduction. The apical portion of the hair cell is bathed in high potassium solution, and the base of the hair cell is bathed in potassium poor solution. This causes the opening of mechanosensitive channels, allowing potassium to flow into the cell, leading to depolarization. This in turn opens calcium channels at the basal end of the cell, leading to vesicular transmitter release to stimulate the.
So this is the same thing with, like we saw exocytosis of the neurotransmitter that required calcium to initiate that, the release of neurotransmitter into the synaptic membrane. That's what we're seeing here.
The nerve. Because the relative voltage and potassium levels are low at the base of the hair cell, potassium flows out of the cell. This establishes the potassium flow through the cell is used for both depolarization, potassium in at the apex, and repolarization, potassium out at the base of the hair cell.
Questions? Right, so let's talk about balance. So the ear, in addition to hearing, is also very important for maintenance of balance. There's ciliated equilibrium sensory receptors located in the utricle and the saccule, which sense tilting of the head when you're doing this. You're doing this. That's what they sense. The semicircular canals, these right here, are going to sense rotating on the 3 different planes. Like a 3D plane, each one of these is in one dimension of a plane. There's 2 types of equilibrium or balance. There's static dynamic equilibrium and linear acceleration when you're going slower or faster. This is sensed by the vestibule. The macula contains receptors within here. And there's an otolith fluid that moves back and forth. Otolith means rocks. They're crystallite, they're crystals, they're rock crystals. Dynamic or angular acceleration, where you're moving in a rotation, are sensed via the semicircular canals and the crista ampullaris receptors within these semicircular canals. When the head is tilted, so just like we saw with those hair cells before, we have same things here. We have hair cells here. And rather than having the tectoral membrane, we now have this otolithic gel-like membrane. So within a gel, there's these little crystals. And so when the head is tilted, that membrane sags, pushing down on those hair cells. And just like we saw in the ear, in the cochlea, it's going to stimulate those hair cells. So this jello on this, pretend that you're tomorrow, some of you are going to be eating jello, I'm sure. Thursday, you're going to be eating jello for sure. Maybe you'll get some tomorrow too, if you're lucky. But here's this plate. And as your head starts to sag, you start to tilt your head down to eat. The jello, the otolith gel, kind of slides on it. And when it slides on it, it opens those hair cells. And initiates action potentials. What we're looking at constantly is a gel that's got these little crystals in it. That's when it sags and when it moves, it's bending the hair cells and initiating action potentials. With dynamic equilibrium, when you're going really fast, in your car, you all of a sudden go from going 30 miles per hour to going 60 miles per hour. That linear acceleration is felt by the sliding of that membrane behind. As it kind of lags behind. The saccule is nearly vertical. It responds to a vertical acceleration. So where you're going really high up, really fast, and then really low, where you kind of get dropped. So what you're really feeling is this membrane sliding along the hair cells, initiating those action potentials. Semicircular canals are going to detect rotary movements via these crista ampullaris receptors. The ducts, the different semicircular ducts, are stimulated by rotation in the 3 different planes. Each duct is filled with endolymph, just like we saw in the cochlear duct. It opens up into a dilated sac called the ampulla, and within the ampulla are those crista ampullaris. The hair cells and the stereocilia, and stereocilia meaning little tiny stiff hairs, are buried in a mound called the cupula, gelatin cupula. And you're feeling when you're moving, we've all done this with little kids. You spin, or you've probably seen someone else do it. If you haven't done it yourself, you should try it sometime. It's really funny to watch. But you spin a little child and you spin them around and around and around. You get up, you know, bear with me. I'll pretend I have a child here with me. My dog, I know, won't play along with this, so. You get a child, grab them by the arms, and you spin them around and around and around and around and around and around and around, and I terrified my cat. But you spin them around and around and around. And then you put them on their feet and tell them to walk straight. You know, it's hilarious because they can't do it. And the reason is because of this cupula within their ears, this perilymph or endolymph is still moving around. And even though they're no longer moving, that fluid is still moving as it's trying to settle down and stop moving. And that's why they can't walk, is because they're still spinning in the semicircular canals. Because this fluid is moving over this crista ambularis and causing it to keep spinning, which makes their mind think that they're still spinning. The cerebellum, how is it involved in this balance and eye and muscle coordination? Paisley, what are you doing? Paisley, come. Pacers, come here. Mom, I would close your bedroom door. So Paisley, come here. Come here, little girl. So the cerebellum is going to integrate vestibular information into its control of muscle tone and posture. You stand up and it adjusts your balance so that you're standing up. It integrates head and eye movement. The nuclei of the oculomotor, trochlear, and abducens nerves are going to produce the vestibulo-ocular reflex, which allows for your vision to stay fixed on a distant object while you continue walking. The reticular formation, remember that's your RAS, so that's your keeping you conscious and keeping you alert and awake. And permanent inactivation of it can cause a coma. So the reticular formation is involved in adjusting your blood circulation and breathing to the different posture changes with balance. Your spinal cord is going to descend via two vestibulospinal tracts, and it's going to innervate the extensor anti-gravity muscles to help you stay standing and not fall over. And the thalamus is the relays information to the cerebral cortex for awareness of position and motor control of head and body. Remember your proprioception? And your head and body. Are there any questions? I want to watch a few more little mini videos just to drive this home. So let's see, which one did I want to watch first? Let's watch the, Watch the utricle and saccule first here.
The human ear
I'm sorry. 1 second here. When it
is
was,
divided into 3 compartments: the external ear, middle ear, and inner ear. The inner ear contains the spiral-shaped cochlea, where sound waves are transduced into neural signals, and the vestibular complex, which contains the receptors for our sense of equilibrium. The central egg-shaped cavity is the vestibule, which contains a pair of membranous sacs, the saccule and the utricle. Inside the utricle and saccule are hair cells similar to those in the organ of Corti. The hairs are clustered in the macula, where their processes are embedded in a gelatinous mass and lie under a thin layer of crystals called otoliths. When the head tilts, gravity moves the crystal mass and distorts the stereocilia of the hair cells. This is how the saccule and utricle provide information about position with respect to gravity.
so it's the way, just the way that membrane is sliding is initiating action potentials. When it slides, it distorts them and they're going to initiate action potentials when it slides along them, opening up channels.
Gravity. Behind the vestibule is the third portion of the bony labyrinth, known as the semicircular canals. The canals project from the posterior region of the vestibule and are responsible for the detection of head motion in 3 spatial planes. The anterior duct senses forward and backward motion. The posterior duct detects moving up and down. The lateral duct senses moving left to right. Each canal contains a membranous semicircular duct where angular momentum is sensed. At the base of each duct is an expansion called the ampulla. Within the ampulla, long stereocilia of hair cells are embedded in the cupula, which sticks out into the endolymph. When your head moves, the endolymph moves the cupula and stimulates the stereocilia.
Any questions? You guys are really quite quiet. Are there any questions?
No.
These next 2 are going to be specifically about the semicircular canals.
This picture here is a picture of a semicircular canal and its ampulla. This ampulla
1 second.
is
Maybe.
depicted right here. And the ampulla, within inside the ampulla of the semicircular canals lies the most important part of this. It's what drives our detection of dynamic movement. And that would be the capula. The capula is this gelatinous mass here that encases the hair cells, which are responsible for contacting the vestibulocochlear nerve and telling us that we're undertaking some kind of dynamic movement. Now, the only way that those hair cells contact the vestibulocochlear nerve and tell you that you're undertaking some kind of dynamic movement is when the capula is actually bent from side to side. And the way that that happens is by making some kind of dynamic movement. When you make some kind of dynamic movement, there is a fluid inside of the semicircular canals that circulates through and pushes that capula from one side to the other, depending on what kind of dynamic movement you're making. So when that happens, the capula gets pushed to the side, and say we're pushing it to the left here. And when that happens, it contacts the vestibulocochlear nerve and says, oh, you're doing such and such dynamic movement. Keep in mind that there's 3 different orientations of semicircular canals, and they're on both sides of the head. So they're not just in the central portion of your skull. They're on both ears. And when you turn one way, both of the semicircular canals are contacted and they're moving. This is how you detect dynamic movement. Now let's look at how to tie in the semicircular canals with the brain, specifically the midbrain, where you find the corpora quadrigemina. The corpora quadrigemina are responsible for.
So this is your colliculi. This is your superior colliculi and your inferior colliculi.
Helping you track moving objects.
You know that it's the second order neurons that are synapsing there.
When you're undertaking some kind of dynamic movement, these semicircular canals actually contact those corpora quadrigemina and tell the eye to move in such a direction so that you can keep track of the things that are moving while you are moving. Because since you're moving, it seems like.
So as you're moving away and you're keeping your eyes are tracking a distant object.
Everything around you is moving, but in reality, everything's staying in place. It's just you're moving. So your eyes are trying to keep track of those things that are not moving. Now, say you were at the top of a hill and you rolled down that hill, and at the bottom, you get down to the bottom and try to stand up and you're super dizzy and you're falling over. So this all has to do with these semicircular canals. These semicircular canals are picking up momentum as you're going down this hill. They're spinning the fluid inside of it. And so the kinetic energy is building up inside this fluid, and it's causing the fluid to continue to circulate even when you have stopped rolling down that hill. So this fluid is continuing to circulate through, and it's pushing that capula, and it's telling your brain that you're still moving even though you're not. So it's telling you that you're moving, it's causing you to be dizzy, and at the same time, it's contacting those eyes, and it's causing them to dart across your face. So the classic, oh, I just rolled down a hill, and then you're looking up at the sky, and the sky's spinning around your head. It's not really spinning around your head. What is spinning around your head is your eyes, because these semicircular canals are contacting the corpora quadrigemina and telling your eyes to keep track of everything as you're moving. But you're not really moving. It's just the kinetic energy inside of the fluid in your semicircular canals is still there.
So are you guys all gonna roll down a hill now and try it out? I know you are. You have to do it now. Watch your eyes try to keep track of everything afterwards. Michaela, I know you
All right,
are.
engineers, in this video, we're going to talk about the
Oh, shoot.
semicircular canals. So again, if you haven't already, please go watch the.
Okay, there. Jesse, I know you're gonna go out and roll down a hill just to see.
Did you call my name?
Yes. Are you gonna roll down a hill just to see?
No.
You know what? Come on. You gotta live a little.
No, my body hurts.
Okay, never mind. You
This
can't
picture
do it.
here is a picture of
All right,
a
I had
semicircular.
to go to the wrong one. Give me 1 second here.
Deep within each ear, there is a balance system called a labyrinth composed of 3 semicircular canals. These semicircular canals are also connected to the cochlea, which is the organ that allows for hearing. Each semicircular canal is responsible for sensing a particular head direction. Each semicircular canal is filled with fluid, and when displacement of this fluid occurs within the canal, nerve signals are sent to the brain informing which direction the head just turned. The posterior semicircular canal shown here detects when the head tilts down towards the shoulder. The superior semicircular canal detects when the head nods up and down in a yes motion. The lateral semicircular canal detects when the head shakes side to side in a no motion. When a person is dizzy, one of the main tests performed to determine whether the inner ear is the source of the dizziness is the Dix-Hallpike maneuver shown here.
Okay.
The head is turned 45 degrees and
Do you have any questions for me about hearing and balance?
No.
It might be kind of unrelated, but so I work in dialysis. Sometimes we have patients who are hypotensive, and when their blood pressure drops a lot, they get that super dizzy feeling, but they're not moving at all. So is that a different mechanism of making them dizzy, or does it have to do with the inner ear?
My mom is overhearing this. Go.
Lack of volume of blood to the brain delivering oxygen.
Lack of volume of the blood deliver.
Lack of volume. It's not lack of volume of blood, it's the pressure that should be pushing the blood. So there's not enough blood in the brain.
There's not enough blood in the brain delivering oxygen.
Because the pressure.
Yeah. Okay.
Because the
But
pressure is low.
is it like tricking the brain into thinking there's movement, or is it affecting a totally different area with just the same symptom? Was my question, I guess.
What?
You just don't think well.
You just don't think well without oxygen.
Okay.
So it's,
Your body's going to start conserving.
yeah, so your body's going to quiet down so that, to stop using that. I mean, there's a lot of.
Okay, so your body is conserving it because you don't have enough oxygen. So it's conserving it, which is slowing down the body, making them feel kind of dizzy. Does that make sense?
Yeah.
It's a good question. Any others?
Have you ever heard of Meniere's disease?
Yes, I have. And what it is it's an increased amount of, I think it's an increased amount of endolymph.
Yeah, my dad has it and he has to watch his sodium intake because that can also throw off his balance with the Meniere's. Just an interesting fact.
Yeah, it's usually, give me 1 second, I'll show you some, I'll see if I can find it really quick. See how quickly I can find it. That's going to be the trick. And I may not be able to pull it up on this site anyway, because this computer is not linked to PowerPoint. All right, let me see here. Let's see what happens. See, it is an it's too much endolymph is being produced. If I'm right.
Yeah, and it creates crystals in the ear or something. And when the crystals shift, it makes you off balance or something. I'm not completely positive.
It's probably because there, is it too much or too little then? Or shoot, let me go back. Amicus. Oh, let's create this. Amicus. Mom, what were you gonna say? Mom? Let's not. I don't know if this is gonna work, but I did, it's too much fluid. And I'm trying to think. And when it comes to the crystals, it's the otoliths that are forming. Most likely. Actually, yeah, it is the otoliths. This may not work because I don't have PowerPoint on here. We'll find out here in a second. Find out. Maybe. Nope, it doesn't work. Oh, wait. Can try. One second here. Okay, it did work. Second here. Come down, come down. So Meniere's disease or Veneer's disease is, can you see this before I
Yes.
start talking? Good. Okay. It's characterized by recurring attacks of disabling vertigo and fluctuating hearing loss and noise in the ear. It's the result of an abnormal amount of endolymph, so it's in the cochlear duct. Possible causes are improper fluid drainage, abnormal immune response, and a viral infection or genetic predisposition. If you have too much fluid, it's going to be difficult to get the right vibrations. Does that make sense, Genesis?
Yes.
And why you would have crystals forming, it has to be the otolith. Or does he know what kind of crystals they are?
I don't think so.
because I would think another possibility is that it's potassium. But I'm not sure. Because if you think, I don't know. No, I'm not going to try to answer that, which type of crystal it is, but it's also the reason that Vincent van Gogh cut off his ear, was for this same reason. He was also a little crazy. What'd you say, Mom? So he was schizophrenic.
Yeah, I was gonna say he was definitely crazy.
But I having friends who have dealt with tinnitus and so forth, I think it could drive you a little crazy.
So
I
it
had
can
it-
cause different
Holy.
sounds in your ears as well.
Oh, really? Wow. Wow. So I know, like I dealt with a hearing aid that didn't work very well, and when it would ring in my ear, I finally quit wearing it because I couldn't wear something that was going to cause noise in my ear just to cause noise in my ear. So I can understand how that would make you a little crazy.
When I started with the tinnitus, I would try and figure out, because it's only ever on one side at a time for me. And
Yeah.
I would be looking around trying to figure it out. And every time I would turn, the noise would move. It took me a while to figure out that it was inside my head.
Wow.
Yeah, that was when I was kind of younger, though. I didn't understand what tinnitus was. I'd never heard of it. When someone started talking to me about tinnitus, I was like, I have that. I know what that is.
I think Aaron, do you have insurance, health insurance?
Yeah, I do.
You should visit an ear, nose, and throat doctor first. Before you go to a hearing aid technologist, go and talk with an ear, nose, and throat person. Because
Okay.
it might, the tinnitus, you may be able to actually work with that, because that by itself can be causing you hearing loss. Does that make sense?
Kind of.
Because it's already resulting in weird symptoms in your ears.
Okay.
One thing may be very much related to something else, the hearing loss. So if you're struggling with sounds that aren't really there occurring within your ear, you may be dealing with something like Meniere's. You understand why I'm saying that? If you looked at that one, it talked about the fact that some of it is fluctuating hearing loss. Do you deal with any vertigo?
No, not for years.
I would maybe first go and see an ear, nose, and throat doctor, see what they tell you. And then, because I'll tell you, hearing aid specialists a lot of times don't know about the anatomy of the ear. And they don't understand the physiology, because I've had some real debates with not my most recent one. I really like her, but my ones that I've had in the past where people don't understand how balance could be related to hearing. And they don't recognize that this structure is all very tightly connected. If this whole thing here is less than a centimeter, this area that's involved in balance has to be less than a centimeter away. I was told that how could I, if you put warm water in your ear, because I told you that wearing a hearing aid, I'm constantly cleaning out my ears because my ear likes to produce a lot of ceruleum, like my mom said, ceruleum. Is that right, Mom? Ceruleum, earwax, as an immune response to my hearing aid being in my ear. And so what I do is I put in the Debrox, which is a hydrogen peroxide derivative, and it clears that out, but then you have to rinse it out with warm water afterwards. And every once in a while, when I rinse out my ear with warm water, I will get nasty, I'll get kind of dizzy from it. And they were sure that was something really, this one place that I went to was sure that couldn't be normal, and that obviously there was a problem. But if you recognize that how close this is to this, when you're washing your ear out with warm water, this is not very far away from this. And you have to get some dizziness when you're affecting the temperature of this area, you're going to affect the temperature of this area.
And if you use cold water, it will make business boom, but probably significant.
My mom said if you use cold water, it will probably make you very, very, it may not make you more than just dizzy, it may make you throw up. Somebody asked me about cochlear implants. Do you remember, was that someone in here?
I don't think it was one of us, but I am interested in those and how they
All right.
work.
Let's talk about that for a minute here while I'm on this screen. So a transmitter and antenna, just like a microphone, is inserted in the skin posterior to the auricle. Posterior and superior to the auricle. The lead is inserted into the inner ear. I can't imagine that doesn't make you sick. Make you a little nauseous for a little while. Because the one thing that I remember when I had my eardrum replaced is that I threw up and threw up and threw up and threw up afterwards. And I'm not, I've been told that we could probably fix my middle ear issue, but I'm not really willing to do it because I prefer to wear a hearing aid rather than go for weeks feeling nauseous. But the transmitter lead is inserted into the inner ear because that's where your hearing cochlea is. The sound waves, and I'm sorry, I'm trying to move the little screen down here. The sound waves are detected by the receiver and turned into electrical impulses. So the receiver is generating the series of action potentials.
So do you have to have a certain type of hearing loss to be eligible to use that?
I'm guessing it has to be a nerve response. It has to be that sensorineural. It won't work on a conductive.
That makes sense.
It probably has to do with, because you can't have, the cochlear nerve has to work because the electrical impulses from the transmitter stimulate the cochlear nerve. So it has to be something to do with the hair cells or the cochlear duct itself, not the nerve. If it's the receptors themselves, that can be worked with. If it's something in here, this is what that will replace. So the implant will replace this. And then it's going to transmit those signals the same way. So it's essentially signaling the action potential, some transmission in the cochlear nerve. You have questions? So a transmitter is inserted into the inner ear. When that transmitter detects the sound waves, that wavelength of vibration, air wavelengths, it's going to transmit that to turn it into electrical impulses that then activate the cochlear nerve. Questions? My guess, looking at the way that transmitter lead is within the cochlea, my guess is it's essentially just recreating this cochlear duct. The organ of Corti is being reproduced. I have a friend who had this done, but I don't know about her experience with it. I should message her and ask her. But it's replacing this and initiating action potentials in the cochlear nerve. Other questions? I should add this slide to our PowerPoint for this one. Let's get started on the autonomic nervous system. Bear with me. Don't know why it's taking so long. Okay, let's get rid of this. Okay. So divisions, remember we had the peripheral nervous system and the central nervous system. Within the peripheral nervous system, we have the somatic nervous system that has to do with skin, muscle, joints, and bones. In the other division of the peripheral nervous system is the autonomic or visceral nervous system, which refers to internal organs like the heart, the lungs, the liver, the stomach, etc. There's one more branch besides the sympathetic division and the parasympathetic division of the autonomic nervous system that has to do with the system of neurons called the enteric nervous system that's going to govern the GI tract. You cannot live without an autonomic nervous system. In its absence, the body cannot maintain homeostasis, and it's fatal. You have the parasympathetic, which is going to reach out and the effectors are going to be the cardiac, the smooth muscle, the gland cells. The sympathetic nervous system is going to be one of the effectors is going to be the sweat glands. Like the parasympathetic, the sympathetic also, some of its effectors are going to be the cardiac, the smooth muscle, and the gland cells. The sympathetic's also going to innervate the renal smooth muscle and the skeletal. Oh, excuse me, somatic is going to be skeletal. If you look here, one thing that we see a lot is ACH. Do you remember what ACH stood for? ACH stands for acetylcholine. And so you see, you're going to see that across all of it's a very common neurotransmitter. This right here is the sympathetic chain ganglion, which we'll talk about. And the sympathetic nervous system specifically also works on the adrenal medulla. Remember, adrenal glands meaning renal meaning kidneys. So these are the glands right above the kidneys. And the adrenal medulla, just like the medullary cavity within the bone, the adrenal medulla is the cavity within the adrenal gland. So the autonomic nervous system maintains homeostasis by regulating the activities of smooth muscle, glands, and cardiac muscle. Most often, polygraphs work because autonomic responses cannot be consciously altered or suppressed. You cannot voluntarily slow your heartbeat to half its normal rates. For the somatic versus autonomic nervous system, the somatic sensory input is your somatic senses. Remember that skin, muscle, and joints, and your bones. Autonomic is mainly enteroreceptors. These are visceral receptors. Remember, visceral means organs. some from somatic senses and special senses. Effectors of the somatic nervous system are skeletal muscle. Effectors of the autonomic nervous system is smooth cardiac and glands. Responses to the somatic nervous system are always contraction of skeletal muscle. Responses of the autonomic nervous system are increased or decreased force of contraction of cardiac muscle, or smooth muscle, or glands. Secretion, increase or decrease secretion of glands. So the autonomic nervous system uses enteroreceptors or visceral receptors located in the blood vessels, the visceral organs, meaning your abdominal, your major organs, your heart, your lungs, your stomach, your small intestines, your large intestines, your kidneys, your spleen, your liver, your pancreas. Some examples of some entero or visceral receptors are mechanical receptors. Remember, mechanical receptors are going to respond to changes in their mechanics. They get pushed open. Chemoreceptors, something binds to them, a ligand binds to them, and they open, or they get activated. Photoreceptors are responding to light. Baroreceptors are responding to pressure. Just like a barometer, they respond to pressure. Thermoreceptors are responding to temperature. Nociceptors are responding to pain. So through the use of these different sensory receptors, the autonomic nervous system can monitor conditions in the internal environment. Just like we talked about with reflexes and the somatic reflexes, we also have autonomic visceral reflexes. And they have the same reflex arc components. You have a sensory receptor, a visceral or sensory fiber, enters the dorsal root ganglion, enters the posterior horn, an integration center that may be a preganglionic neuron, preganglion meaning before a ganglion. What's a ganglion? Ganglion is where the cell bodies are synapsing with incoming neuronal signals. And then we have a preganglionic axon, or the efferent axon, and then the visceral effector, and then the response. So we have the same components we've seen in all reflex arcs. The sensory neurons are going to carry nerve impulses from the stimulated sensory receptors in the visceral organs to the central nervous system for integration. The autonomic motor neurons are going to carry impulses from the central nervous system to the smooth muscle, cardiac muscles, glands. An example of a visceral reflex arc is a baroreflex. So this what does a barometer measure? You've heard of barometers. What do barometers measure?
Atmospheric pressure.
Okay, so they measure atmospheric pressure. A baroreceptor is going to measure pressure within the organs. We have specific baroreceptors in the internal carotid arteries. right up here. Also in the aortic arch right here. That are going to sense when the blood pressure has increased. They send a signal via the glossopharyngeal nerve to the medulla oblongata. Remember, that's the area where we have the cardiac rhythmicity center. And the cardiac rhythmicity center is going to activate the vagus nerve to transmit an inhibitory signal to the cardiac pacemaker in the heart, inhibiting the heart's slowing down its contractions, which is going to result in the heart rate decreasing, which is going to decrease the blood pressure. So receptor senses it, sends a signal via the glossopharyngeal nerve. Glossopharyngeal nerve interacts with the integration center, which sends a signal out, an efferent autonomic neuron signal via the vagus nerve that's going to transmit inhibitory signals to the cardiac pacemaker to slow the heart, reducing the blood pressure. Questions so far? We have a lot of dual innervation where the sympathetic and the parasympathetic divisions are innervating many of the same organs. So they're both, one is going to speed things up, one is going to slow things down. The different effects, the excitatory or inhibitory effects, are due to the different types of neurotransmitters and the different types of receptors that those neurotransmitters can bind on effectors. So remember that neurotransmitters can be excitatory or inhibitory sometimes based on what receptor they bind to. The receptor is what's going to dictate the action that that neurotransmitter produces. So we have both the sympathetic autonomic nervous system and the parasympathetic division, both acting on multiple organs simultaneously. For example, we have parasympathetic fibers via the oculomotor nerve that are stimulating the ciliary muscles. No, sorry, the pupillary constrictor muscles within the iris. And they cause the pupil to constrict. So parasympathetic causes the pupil to constrict because it relaxes the muscles of the iris, making them small. The sympathetic nervous system also acts on those pupillary muscles and relaxes them. Sorry, it activates them, causing them to constrict, causing the pupil to dilate. So both the parasympathetic is acting on the pupillary constrictors to relax them. The sympathetic fibers are acting on those pupillary constrictor muscles to contract them, causing them to become shorter, causing them to dilate. Questions? So sympathetic is going to relax it. Parasympathetic is going to relax it. Sympathetic is going to activate the constrictor muscles, causing them to become shorter, causing the pupil to look dilated. Questions? So these two different divisions can work on the same organs. The sympathetic nervous system is going to be involved in fight or flight. It's going to prepare the body for intense action and is concerned with processes that expend energy. The parasympathetic is rest and digest. It relaxes the body and inhibits the slows the many high energy functions. Its activities are concerned with restoring and conserving energy. The sympathetic response, this fight or flight, is stimulated by 4 E's: an emergency, excitement, embarrassment, and exercise. When the sympathetic nervous system is activated, the heart rate increases. The liver releases glucose into the blood. You got to increase the blood glucose level so you can run away from the bear. Hopefully be faster than the guy behind you. The bronchioles of the lungs dilate to allow you to get more air into your lungs, allow for better air perfusion, ventilation. The pupils dilate to bring in more light into the eyes. The adrenal glands, those glands that are right above the kidneys, are going to secrete epinephrine and norepinephrine, which have the same effects as the sympathetic neurons, but their effects are longer lasting. Digestive activities are inhibited and the bladder relaxes. With the parasympathetic nervous system, the heart, in opposition, the heart rate decreases. The liver no longer releases glucose, and it produces bile, which allows for lipid absorption from the small intestines. The bronchioles of the lungs constrict, so there's less air going, less ventilation. Pupils constrict, letting less light into the eyes. The adrenal glands stop secreting epinephrine and norepinephrine. Digestive activities are stimulated and the bladder contracts. The body calms so it can recover from the heightened physical activity and promote restoration and repair. Any questions? Which of the following effects are mediated by the sympathetic nervous system?
C.
C. Yes, increased heart rate. Which of the following are mediated by the parasympathetic nervous system?
Would it be A?
Yes. Stimulation of the digestive system. The sympathetic nervous system and the parasympathetic nervous system are two divisions of which other nervous system?
Would it be C as in cat?
Why would you say C?
I'm not completely sure, but I just feel like what we were talking about would be sensory.
Okay. It's actually, I think it's the autonomic. It's E. Do you see why?
Sure.
Because they're both divisions of the autonomic nervous system. Any questions so far? So the autonomic nervous system has components in the central nervous system and the peripheral nervous system. There's control nuclei. Remember, those are the organizations or congregations of cell bodies in the hypothalamus and other brainstem regions. There's motor neurons in the spinal cord and peripheral ganglia. And there's nerve fibers that are going to travel through the cranial and spinal nerves. In the somatic nervous system, the effectors are always skeletal muscles. They're always myelinated nerve axons, nerve fibers, and they always secrete acetylcholine. And acetylcholine is always excitatory. In the autonomic nervous system, the preganglion before the ganglion is myelinated. The postganglionic fiber that's going to reach out to the effector is unmyelinated. And the autonomic nervous system effectors are cardiac muscle, smooth muscle, and glands, and the effect can either be excitatory or inhibitory. So somatic effectors are always skeletal muscle, always usually voluntary. The endings are going to be neuromuscular junctions. The transmitter is acetylcholine. It's always excitatory. The effectors for the autonomic nervous system are glands, smooth muscle, and cardiac muscle, usually involuntary. The neurotransmitters can be acetylcholine or norepinephrine, can be excitatory or inhibitory. And there's 2 nerve fibers in the autonomic nervous system and 1 in the somatic nervous system. Would autonomic postganglionic fibers or have a higher or faster conduction speeds than somatic motor fibers? What do you know about myelinated versus unmyelinated fibers? What are the conduction speeds like?
Signals travel faster through myelinated than
That's
unmyelinated.
right. That's right. So it's going to be faster through the somatic. Keep that in mind. So stay with me for 2 more minutes here. Preganglionic neurons is going to be the first of the 2 autonomic motor neurons. So it's going to come out pre, meaning before the ganglion. The cell body is either in the brain or the spinal cord. The myelinated preganglionic fiber is going to pass out of the central nervous system as a part of the cranial nerve or spinal nerve. Here. And it's going to extend to an autonomic ganglion, just like the dorsal root ganglion. It's going to be where we're going to get synapses of axon terminals with cell bodies and dendrites. In that ganglion, it's going to synapse with the postganglionic neuron that's unmyelinated. Acetylcholine is always going to be released here. That's the neurotransmitter here. The postganglionic neuron is the second of the 2. It lies entirely outside of the central nervous system. And its cell body and dendrites are located in the autonomic ganglion. It's going to synapse with 1 or more preganglionic fibers. And it's unmyelinated in its axon. And it's going to terminate at the visceral effector. Have questions for me? So preganglionic is myelinated. Postganglionic is unmyelinated. Postganglionic neuron is completely outside of the central nervous system. Preganglionic fiber extends from the central nervous system out via one of the spinal nerves or cranial nerves. Have a wonderful Thanksgiving. We will start here again next Tuesday. Enjoy your day.
You too.
You too. Happy Thanksgiving.
Happy Thanksgiving.
Happy Thanksgiving.
Good Thanksgiving.
Thanksgiving.
Professor,
Yeah,
I just have a question before we get off.
go.
When was our case study 2 due? Because I feel like it was already due.
I think it was due December 1st.
December 1st. Okay.
I can't honestly remember, but I think December 1st sounds like a good date.
Okay.
Why don't we, and you'll notice, Miranda, I don't close those.
Okay.
I don't, because too many people are going to submit things late. I don't close them. Because that just means I constantly have to reopen them.
Yeah. Okay. Well, thank you for telling me.
You're welcome.
Have a good day.
You too.
I wanted to piggyback that with another question, if that's okay.
Okay.
I've been having some issues with the smart book assignments. I've been like submitting them, but I haven't been getting credit. Like
let me interrupt you just for a second, Terry. Is it giving you a score?
No, see, like I'm doing the entire assignment and then it's giving me a 0 out of 10 a couple days later. So like when I started the 13 after it was due, but it's still, you know, like when you start the assignment, it will tell you if you're like past due. It didn't tell me that. So I went through it and did it. And the reason why I'm asking that is because it's whatever if I get credit for it or not.
It isn't whatever because it adds up.
Yeah, for me, it was just because like those, I'm kind of teetering between an A and a B right now. And I just want to make sure that I finish the semester strong, given like
I'm gonna stop recording for 2 seconds. Give me one
Okay.
second, okay? You're the only one here, so give me 1 second here.
Okay, thank you.
I have to figure out how to stop recording. Give me a moment. Maybe this is what I need to do. Stop recording. Okay.